All right, in the previous unit, we talked a lot about propagation in free space. Now I just want to talk a little bit about propagation in more realistic environments, that is, environments with obstacles. I'm just going to give you a little bit of a qualitative description of some of the mechanisms, but there are a lot of references, and maybe I'll provide some of these, which you can get into more of the details for the mathematical modeling. So the first mechanism that I want to talk about is reflections. And to an electromagnetic theorist, a reflection occurs at what you would call a dielectric interface. That is any place where there's a change in the characteristic impedance, as I've shown here. So maybe, for example, going in free space, where a wave impinges upon a material like a metal or concrete or so on. Now, when you want to try to mathematically analyze what happens at one of these reflection boundaries, you typically have to consider two different distinct cases, or depending on the polarization of the electromagnetic wave relative to the plane of the interface. So what you typically look at is what happens to what's called the parallel polarization, where the H field is in that plane and the E field is perpendicular, or the perpendicular polarization, where the E field is in that plane and the H field is perpendicular. Now, you can work out the just using some basics of electromagnetics what happens, and you will see that the reflected components have two parts. There's what's called a reflected component, which will basically bounce off, and that reflected component will always have the angle of reflection equal to the angle of incidence if this is a smooth surface, just like you would imagine just from geometry. But there'll also be a second component, what's called the refracted component or the transmission component, which will go into the second dielectric medium, and that will actually bend at an angle which is given by this classic formula here. Now, in certain cases, there's actually no component depending on these signs of these angles. Also, there will be a gain. In addition to these angles, there will be a complex gain associated with both the reflected and the transmitted components, which are typically represented by lambda and t. And these are complex numbers which will typically depend on the characteristic impedances. Now, one aspect of this is that since in general the perpendicular and parallel components get reflected in different manners, the relative gains can change, and hence the polarization of the reflected wave may be different than the polarization of the incident wave. Now, a very important special case of this, by the way, those formulas came from this very excellent set of lecture notes that you can read here, and I've put the links in the file, is the special case of a metal reflector. So that would happen, of course, any metallic material. And a metal, because it's a pure, perfect conductor, should have a characteristic impedance of 0. So if you just substitute that into the formulas that I had shown in the past, you'll get that all the signal is reflected back. So it's really a perfect reflector. And there's no transmission component. The other aspect of this is that since all the signal is transmitted back, the polarization is always maintained on the reflected component. Now, there's a lot of literature about various types of measurements of actual practical building materials. So if you want to model this, you can look these up in various websites. I've just put here from one source of reflections and attenuations or transmissions through at 2.4 gigahertz of different materials. So here you see, for example, wood doors, steel doors, and so on. And you can see here that there's a range of different attenuation levels that you get going through these materials. At least at 2.4 gigahertz, eventually your signal will penetrate through all of these, just at different levels of attenuation, maybe about between 5 and 20 dB. You can even go through brick and concrete, for example. At higher frequencies, that's not possible. But if you do want to model these things accurately, you have to pay attention to some details, for example, that the thickness of the material and the actual type of the material. The next type of attenuation that I want to quickly talk about is atmospheric absorption. And this is particularly important to model correctly if you're looking at long distance transmissions in the millimeter wave bands. So for example, if you have a long distance point-to-point link, definitely a satellite link. Now, there's a whole theory about mathematically modeling the effects of water absorption, but luckily MATLAB's phased array toolbox gives you some excellent models that are built in, so you can look at various types of losses as a function of the frequency and the atmospheric conditions. So here I've plotted a few examples. One is the loss due to rain fades, and that will in general depend on the level of the rain itself, so you can put that in, for example, here. You can also plot, for example, the atmospheric loss, and you'll see that the atmospheric loss have these spikes in them, and those spikes come due to particular resonant frequencies of the molecular absorption of the atmosphere. You'll also see that the level of that loss will depend on the dryness or humidity of the air, and it'll be higher when the air is more humid. You can see that at higher frequencies, say at 100 gigahertz, these atmospheric losses can become particularly large in these resonant bands. For example, around here, you'll see that this atmospheric loss is over 10, 12 dB per kilometer. Although if you're looking at short cell deployments and you're looking in bands that are under 100 gigahertz, with the short cell sizes maybe in 100 to 200 meters, these are typically not relevant. But if you're looking for a longer distance link, like I said, a point-to-point link or a satellite link, then these definitely need to be considered. All right. One last thing that starting 1, 2, and 3. One last thing that I want to talk about in terms of reflections is what's called specular versus diffuse reflections. So a specular reflection occurs whenever the material is very smooth. In this case, it'll follow that model which I just stated earlier. There will be a single reflected path whose angle will equal the angle of incidence. But if the surface is rough, and by rough meaning that the variability in that surface is on the order of the wavelength of the incident beam, then that roughness can cause a large number of reflections at different angles. And this will be very important to model when you're looking at trying to predict propagation. Now that I've talked a little bit about reflections, I just want to quickly talk about an important concept called the radar cross-section. So this is very relevant, of course, when you're trying to do radar, but it will also help us understand propagation in certain communication scenarios as well. So in the radar cross-section, what we have is, imagine there's a transmitting radar antenna. It sends a incident wave and it hits a target, and then you have a receiving antenna, which could be the same as the transmit, or it could be spatially at a different location. So to analyze this, let's just say Wi is the incident radiation density. So remember that the radiation density will be just the power per unit area. And let's say somehow that this area has the total reflected power then will be some kind of sigma times the incident radiation density, where sigma represents kind of the effective area captured by that reflection. So if that's the case, then at the receiver here, that scattered density will be that reflected power divided by 4 pi r2 squared, this distance here. So if this intuition is correct, that way by just solving here for sigma, we can define the radar cross-section as this ratio of the scattered to the incident densities multiplied by this distance r2 squared. And that defines this effective radiation target for any receiving target. Now, in general, this radar cross-section here will depend on the angle, and I'll show you some examples momentarily. Now, before I do that, though, if we have to define this idea of this radar cross-section, we could very easily get a relation between the received and transmitted power given by this formula here, which I'll show in prove in a couple of slides. But let me just show you a few key aspects of this. The first part about this is that if you look at this term here, it decays proportional to the product of R1 and R2 squared. So if these were the same, this would actually decay as 1 over R to the fourth. So it decays much faster than the decay in free space, which is 1 over R squared. Similar to the free space equation, though, you do get a gain, which is related both to the directivity of the received and transmit antennas, and the total power will also be proportional to this radar cross-section. Okay, let's just prove this. It's actually pretty straightforward based on these definitions. So let's look at the incident wave density coming into the target. We know that will be, if you had a uniform transmission, it will be the transmit power divided by the surface area of the sphere at this distance, and then it will be multiplied by that antenna directivity. We know from the definition of the radar cross-section that the reflected wave will just have the power density of sigma times the incident wave divided by that distance squared. So when you substitute that incident in here, we get this. But we know also that the received power will be the aperture of the received antenna times the scattered wave density. And then we use that antenna directivity relationship that we proved in Unit 1 to say that the received aperture will be the directivity times lambda squared over 4 pi. When you put all that in, we get the radar equation from the previous slide. So just to show you some examples of radar cross-sections, the first table here is shown from Balanis, and the text, and you'll see the radar cross-sections, first in linear units, but also typically more commonly done, which is in dB per square meter. So you'll see that a large truck, for example, can have about 200 meters squared. So it's actually, in this case, it's quite a bit bigger than the physical size of that truck. And depending on the angle, you see that the automobile is 100 meters squared. Humans become much smaller, down to about 1 meter squared. An insect is, maybe about 0.01 meters squared. And tactical fighters, which are designed to try to avoid detection, can have almost negligible radar cross-sections so that they become almost impossible to detect. You can also analytically work out the radar cross-sections for a few simple objects. You'll see that in some cases, like for sphere, the radar cross-section is closely related to the area, but that's not always the case. So for example, if you take a flat square like this, its radar cross-section actually depends on the wavelength because it decays at 1 over lambda squared. So it's 1 meter squared at 10 gigahertz, but it's actually much smaller than that at 1 gigahertz. This paper here was from an excellent co-author of mine, Vasily Semkin, in Finland, and he actually measured, in this case, for example, some radar cross-sections of drones. I just put this up to show you, in this case, the strong angular dependence that you will typically get when you're looking at any type of radar cross-section. So it actually matters the angle by which you're seeing that drone. There's a strong high radar cross-section in certain angles, and it turns out those are angles where you're hitting the metal battery of that large metal battery. At other angles, that radar cross-section becomes a lot smaller. So if you're interested maybe to do a radar project in this class, you can get this kind of data and try to make some simulations to see whether you'd be able to, for example, detect a drone. And we might do a little bit of radar as one of the lab exercises in this class. All right, another aspect I want to talk about as an impact of reflections is how the path loss coefficient changes. So one common type of reflection is what's called a ground bounce. So imagine here there's a transmitter and a receiver, and there might be a direct path, but then there may be a reflected path off the ground. Now, remember that in free space, we saw that the density decays as d squared, because d squared is because the area of a sphere in free space is proportional to d squared. But when you have ground reflections or other types of reflections in that environment, generally the power can decay at a rate faster than d squared, right? If we say that if it decays at d to the alpha, we call that parameter alpha the path loss exponent. And sometimes it can actually be less than 2, but typically it's between, say, 3 and 5. The less than 2 happens typically in what's called a wave-guided environment, like a road in Manhattan, say, where it's the signal's being directed by the buildings. It can also be shown that in this very simple case here, where there's a single ground bounce off an infinite ground plane, and you get it at a certain distance, that actually turns out to be exactly, as you get far away, alpha equal to 4. I'm not going to derive it in this class, but there are several references you can do to look that up, and you'll see it here. Now, something just about the impact of these path loss exponent. So if you're in a coverage limited system, typically you want that path loss exponent alpha to be small, because that would mean that the path loss is decaying at a rate slower with distance. So that means that the power decay is slower and the signals have a greater range. But interestingly, in interference limited systems, you actually want the alpha to be high, and we're going to return to this point later in the class when we talk about, for example, cellular systems. Just to give you an example here, suppose there's a cell phone and it's receiving signals from 2 base stations. One at a signal D1, at the same time it's getting an interfering signal from a base station 2 at a distance D2. So in that case, the SINR will be the power from the desired signal divided by the noise and the interference. But let's say that we're in a interference limited regime where the interference is much smaller. So then that SINR will just be P1 over P2. But if these are decaying as d to the minus alpha, you get this ratio here. So as you get closer to this base station, this ratio d2 to d1 will grow, and then you want this alpha to actually be as large as possible to give the highest SNR, so it can isolate systems. So we'll return to this quite a bit later when we talk about cellular systems to try to look at the impact, but just to keep that in mind for now, not always you want a low alpha. Another type of mechanism that I want to talk about, or just at least briefly mention, is diffraction. So diffraction concerns what are called interfering objects. For example, this plane here, but many environments would have interfering objects. For example, walls and buildings and so on. Now it turns out that because of the wave nature of radiation, that the propagation around these interfering objects is not sharp. Instead, what will happen is that there will typically be some component of the signal that you will get even when you're in non-line of sight with the original path. So just to give you an example, let me show you this example here of what's called knife edge diffraction. So knife edge diffraction, it describes a case when you're looking at diffraction around a semi-infinite barrier. So here's the edge of the barrier is here, and imagine that this blue plane goes on infinitely on both dimensions and down. Now consider a point here where you're a distance h from that barrier. As if you were looking at it just from sort of geometrical ray optics, if you so like, what would happen is when h is 0 or positive, you would be able to see the transmitter clearly and you'd get a perfect line of sight signal. But as soon as h were negative, what would happen is that this barrier would be blocking it and you wouldn't see anything, so the path loss would be infinite. But that's actually not what exactly happens. Instead, you get this relatively slower transition. As you start off from the line of sight points, it actually starts to oscillate, and then as you hit the barrier, it decreases, and then it decreases at some rate. The parameter for this here, which I've listed as nu, is dictated by what's called a normalized excess path length. This is the path length here. This is the path length, excess path length, relative to the number of wavelengths in essence, and I'll maybe have you do a homework problem to work this out. Now, just a couple of things about this. If you notice this normalized parameter here, you see that the wavelength in this case is on the denominator. So if you plotted this back in terms of the actual distance, this transition would be much faster at very small wavelengths. So the diffraction effect becomes less. And for this reason, you may have heard, for example, systems move up into the millimeter wave bands, the opportunity of diffraction actually decreases, but it's still definitely present. You'll also see that because of this d1 plus d2 on the top and a d squared on the bottom, the rate of that diffraction will actually decrease as you get further away from the barrier. Now, just a very nice experimental sort of evidence of this. This was actually done by a graduate student here at NYU under my colleague Ted Rappaport. So they were at this time looking at 73 gigahertz diffraction around a human body, with one of the key obstacles in the millimeter wave bands. So in this case, the graduate student, George McCartney, was walking between a transmitter and receiver at different distances between the transmitter and receiver. And as he was walking, he recorded the signal strength, and you can see again that it's not, in this case, the millimeter wave bands are not actually penetrating his body. There's very little penetration. So almost all the signals that you're seeing are actually diffractions around the body. But you see that it's not abrupt. Instead, you have this relatively slower transition here. Now, just in this case here, we'll see a couple of things I want you to look and notice. One is that the total drop can be fairly significant, down to 20 to 40 dB, but the level of that drop will depend on the position that he's in. You see that ringing effect here, and that's actually just like the knife edge, single knife edge diffraction that we saw earlier. Also, this is not plotted as a function of distance, but is plotted as a function of time with the person moving. You see that it's decaying, and it decays in the order of hundreds of milliseconds to go from that peak down to the valley. We're going to talk a lot about adaptation of various systems, but we'll see that actually in practical wireless systems, hundreds of milliseconds, although that's very short, by human times is very fast, and wireless systems can easily adapt to that. So at least in the case of human speed motion, this wouldn't be a problem to adapt to, provided that at least there's some other path or something like this to recover from that 20-30 dB fade. All right, the upshot of all of this is that in real environments, radio waves have many actual paths. Just this, for example, this cartoon here. There's a car driving around buildings. You can get direct paths, but it can also get diffracted paths. You can get reflected paths, and maybe even it can get a path that might actually go through a material if that material was sufficiently thin. So that wraps up all I'm going to say about propagation. This is a huge and super interesting field. Feel free to look up more, but just to give you a qualitative understanding, I hope it gave you some ideas, and you can test them out with this very simple exercise. Just grab this random floor plan from the web, and I imagine hypothetically I put an access point, say, somewhere here in the living room, and I want you to try to just pick one point for each of these possible transmission mechanisms where a receiver might get this. So where could it receive, for example, a direct line of sight path, a reflected path, a diffracted path, and so on, and try to draw that path. Of course, in many locations in reality you would have multiple different paths, but as long as you can just identify one. There's no single correct answer for this, but just give you a kind of simple idea. Okay, and when you're done with that, go on to the next unit.